So last time we defined an infinite set to be countable, or sometimes folks say enumerable, when its elements can be labeled 1, 2, 3, 4, 5, 6, 7, so on and so forth. That is, when the elements in the set can be put into one-to-one correspondence with the positive integers, or the natural numbers, whichever you prefer to do. So, even though countable sets can contain the positive integers, like the entire set of integers, it's still countable. There's ways to make gaps big enough. When you're talking about infinity, you can sort of create gaps that are big enough to handle other countable sets. So the proof for the integers being countable looks kind of like this. Element 1, call it 0. Element 2, call it 1. Element 3, call it negative. Or negative 1, call it element 3. 2, call it element 4. Negative 2, element 5. And in general, element 2k is number 2k. And element negative k is number 2k plus 1. So the integers is countable. So even though the positive integers is a proper subset of the integers, z plus and z have the same cardinality, the same size. That one's like easy enough to believe. The one that is, counterintuitive is the rational numbers. The rational numbers is still countable. As a matter of fact, a set bigger than the rational numbers is countable. The set z plus cross z plus, Cartesian product z plus. It's the set of all ordered pairs a, b, such that a, b are both positive integers. And once you show that one is countable, then you can add in 0 and the negative of the rational numbers by doing that same alternating trick we did for z. And the proof for that is right there. All right, you write out all the pairs of rational numbers in a two-dimensional array like this, and then you order them as follows. You just use these triangles here. Number 1, number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Eventually, when you keep doing these diagonals, even though they keep getting bigger, they're all finite, and eventually you reach, any element that you want in this big two-dimensional array. So the rational numbers is countable. However, there are non-countable sets, uncountable, too big. Oh, so in this sense, Q and Z plus have the same cardinality, even though Q is huge. R, the set of real numbers, is not countable. Now we're using a few assumptions here, but it'll work out fine. So let's show that I, the interval from 0 to 1, closed interval, which is a subset of R, is not countable. Therefore, R itself can't be countable. Because if you counted up the whole of the real numbers, you would have counted up the interval from 0 to 1 along with it. All right. Proof by contradiction. So when you want to prove something is, well, in this case, you want to show that this I is not countable. So you want to show that. So to do contradiction, you want to assume that's true, that I is countable. You assume the opposite, the negation. So every real number in I has a unique and infinite decimal sequence, and every infinite decimal sequence is a real number. Is a unique represents a unique real number. real number, whoops, as long as we exclude an infinite repeating 9. An infinite repeating string, an infinite sequence of 9s, an infinite, sequence of consecutive 9s. Right, like 1/2 is 0.5000, 1/3 is 0.3333, 1/6, 0.161616, 1/7 is 142.857. This number here, that's a real number. You can make these 1s into 9s if you want. That's fine. And this doesn't cause any non-uniqueness problems, but you don't want to use any concluding sequence of 9s because essentially it turns into a 1 in the next decimal place. So like 0.99999 repeating is actually 1. 0.099999 is actually 0.1. So, but that's the only non-uniqueness that happens with decimal expansions. And then the proof that 0.999 is 1 is right here. That's a proof that it's 1. Somebody noticed another one. If you take 1/3 and multiply by 3, you get 1. But if you multiply this by 3, you get, well, it seems like you get 0.99999, right? Actually, we don't know how to multiply infinite expansions. But, it certainly would seem that way. All right. Is that somebody's asking me something? Or?
Yeah, I had a question.
Yeah.
Does this mean that if we were to fictionally assume that infinite repeating 9s did not equal 1, that the real numbers would be countable? Like, is that the only exception?
Oh, no. There's other examples like this. Okay. There's other no. This is just something specific to the real numbers. It doesn't. It could be just real numbers that use zeros and ones. Forget about 2 through 9. Just use zeros and ones. That's still uncountable. So all real numbers that just have zeros and ones in their decimal expansions, that's uncountable too. But, this is something more familiar, so I'm just using that, okay? So now, by way of contradiction, right, assume that I is countable. So there is a labeling of its elements in the following fashion. Now, normally what you should do is write the following. So like I should write it like this to be more general, but I don't want to do that. I just want to give you a good feel for what's going on here. So you're going to have some number here. So 0.61539827775643210015 blah blah blah. Element 2 is going to be 0.715499990998765431, so on and so forth, whatever it might be. Number 3, oh, maybe that's 1/3. We'll put 3, 3, 3, 3, 3, 3. You know, you're gonna have. I'll put a 4 here. And number 4 is going to be some other real number in the interval from 0 to 1. You know, and we can write it more generally. D1, D2, D3, D4, D5, D6, D7, digit, D for digit, D8, D9, D10, D11, D12, D13. Going on like that. Number 5 is going to be 0.190012314598714149, so on and so forth like that. Okay. And onward it goes. That was element number 5. Here's element number 6. And it goes on and on like that. Okay. So we assumed countability, and therefore we have this listing of all the real numbers in the interval from 0 to 1. Why would that be wrong? I mean, if it was wrong, if we didn't actually have a listing of all the real numbers in the interval from 0 to 1, what would happen? We would have had to have what? Missed one. We would have had to have missed one. How do we find one that we missed?
Just throw an extra digit in anywhere you want.
You got to be real specific. Got to be real specific. Take the first digit, the digit in the tenths place, here. In the next number, take the digit in the hundredths place. In the third number, take the digit in the hundredths place. In the fourth number, take the digit in the 10 to the minus fourth place. In the next one, take the digit in the 10 to the minus fifth place. Right? And keep going like that. Okay. Let P1 be an element of the set of base 10 digits. Or 9. Let P1 be an element of the digits from 0 to 9 that we use in base 10, which is different from element 1, the digit of element 1, in the ten to the minus 1 decimal place. Let P2 be a digit from 0 to 9, which is different from the digit of element 2 in the 10 to the minus 2 decimal place. let P3 be a digit, which is different from the digit of element 3 in the 10 to the minus third decimal place, etc., etc., etc. Now, come on, 0.P1, P2, P3, P4, P5 is an element of what? Of what set we talking about here?
Set of numbers from 0 to 1.
Yeah, it's an element of I. But, so what should we call it? Let's call it M. M equal to this is an element of I. Make that better. But M is not listed above because why? Why is it not in this listing? Right, so in this listing, like P1 is going to be something other than 6, 5. So is the number M equal to this first guy?
Okay.
Is it equal to this first guy? Pick the first decimal place of this number M to be different than 6. 4. So is M going to be equal to the first element in this listing? If the first decimal place is 4? I mean, if M is equal to 0.4 something, 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 is it equal to this guy? Come on, folks. M is 0.4 something, something, something. So is M equal to this number here?
No.
No. They have to have the same digit. They have to have the same digit. Okay, for the second decimal place of M, pick something other than 1. 6. So is M equal to this guy?
No.
Equal to that? No, can't be. It differs in the second decimal place. For the third digit, pick something other than 3. 4. So is M equal to this guy?
No.
No. No way. So on and so forth. It's not going to be equal to him. It's not going to be equal to this one because it differs in this decimal place. So on and so forth. So M equal to P1, P2, P3, P4, P5, blah, 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 is between 0 and 1. But M is not listed above because it differs by at least one digit from every number listed. It always differs by a digit. Two real numbers must have the same digit expansion, same decimal expansion. The decimal expansions, the only non-uniqueness that happens is when you get that 0.99999 thing going. Just don't use it. Well, what did we assume? What did we assume about that listing?
it was every number?
Yeah, that we did hit every number in 0, 1. But this isn't. Or every number in I. But this is number in I, and it's not there. Right? This is a number of I, but M is not listed above. But the listing was supposed to be was assumed to be all elements of I. A contradiction. So that's it. So the real numbers is not countable. So therefore, I and R itself are uncountable, not countable. So now I want to just let you know about. So there it is. I mean, there are infinite sets that are bigger than other infinite sets. So some infinities are bigger than other infinities. Right? So in this sense, an infinite set R is bigger, has bigger cardinality than infinite set Z plus or N. So here's what's something known as the continuum hypothesis. Continuum hypothesis says the following. So and I forget how to draw it. I think it's like a backwards N or something like that. Do I have it in my notes somewhere? It's the aleph. You know how to write an aleph? Yeah, it's like a backwards N with some tails on it. Wait, did I just do that wrong? Gosh. Yeah, I got it backwards. Yeah, it's like a regular N. Okay, so let aleph N be the cardinality of Z plus. And then let aleph 1 be the cardinality of just the cardinality of R. So this is used for those. These letters are used for to stand for the cardinality of these sets. The continuum hypothesis states that there's no set whose cardinality is strictly between aleph 0 and aleph 1.
It's 121, by the way.
Oh, I'm sorry. I got carried away. Between Aleph 0 and Aleph 1. Okay, all right, guys. So we'll see you on Wednesday. We'll talk a little bit more about the homework if necessary, and then we'll move on to Chapter 4. Okay, guys. Have a good afternoon, and we'll see you on Wednesday.